suivra. Et donc là, c'est en train d'enregistrer. Tu peux y aller.
Okay, so I guess we'll do it in English. There are a couple of non-French speaking people here. So hi everyone. So today I will give a brief introduction to Ensemble method.
Stop. Tu enregistres, Fabien?
Yes, it is recording.
Yeah. I didn't see the sign. Okay, sorry.
And so these are methods of machine learning. So as a disclaimer, I'm not at all an expert in this, but I was curious about the efficiency of this method that are in general top method in competition, let's say Kaggle competitions. You have heard probably about random forest and XGBoost. So I was curious about that, and also about their ability to explain their decision, which is not the case of other techniques if you think of a neural net, for instance. So here you have some explanation of what features matter for the decision. So this is an interesting property of these methods, and so that's why I thought this reading group was a good opportunity to better understand what is behind this method. So feel free to interrupt me if there are questions. It should be quite, easy to follow, I hope. So we are in the field of supervised learning, which means that the objective is to predict some label. Let's say if you have a classification task, or a value, which is called a regression task of an object by training. Okay, so you have a lot of examples, and you need to learn the mapping, some mapping represented by this function f from x to y, and so x here is so it was used to be so. Yes. So x here is some object characterized by d features, d numerical values, a vector, and from that vector you need to decide what is y, and y could be a binary, it could be in a set of finite set of labels, or it could be a real value. And so you have a training example for that. N examples, and of course you need to decide how, the quality of your prediction, and for that you have some loss function, and so what you do is you just evaluate the quality of your prediction through the empirical mean over the training example, and you try to minimize this empirical loss. And you have also this omega function, which is an optional regularization function, so that you don't look for too complex function, like to have some constraint on your function.
I have a question here, Thomas.
Yes.
I don't understand very well this function because it doesn't depend on the samples, so I don't understand what it does in the minimization.
You mean omega?
Yeah.
So you will see examples later, but let's say if you like to predict, let's say a 1D function, you have a polynomial, you may fix, you may have penalization for high order polynomials, for instance.
Okay. Yeah. There was something I didn't understand. I understand now. It's the parameter here for the minimization. So.
Yeah.
Yeah, it's okay. Sorry.
But we'll see example later. So this is a very simple example. So here, let's say, why don't have a black? Don't have a black. I don't understand why. Well, let's say. So here, each object is characterized by two features, two values. So we are dimension 2, and you need to predict binary labels. So here the color, it could be blue or red. And you have 100 samples. And so basically what you have to do here is to partition the plane so that, for instance, you may decide that given your samples, everything on the left would be red, on the right would be blue. And so, of course, there are many ways to do that, and to do that perfectly, let's say, for your training examples. But the objective is to be able to generalize, so that when you have new sample, you have the good decision. And this is where the regularization matters. So probably you would prefer a smooth function rather than some very complex function that may overfit on your data, on your training example. And so a very famous and basic way to do that, and as an example, is decision tree. And a decision tree is just a recursive split of the training set that maximize loss reduction. So let's give an example. So here, for instance, I will choose a feature. So let's say I have x1 on the x-axis, x1 and x2. And so I may, for instance, choose x1 and give a threshold. So let's say t1. And so at the root of the tree, I will check whether x1 is less or higher than t1. And this is so it will be the binary tree this way. And so maybe I will decide on the left that all the samples are blue, and I will decide blue, and on the right I will decide, on the left I will decide red, and on the right I will decide blue. Okay, and I will do this recursively. So on the left I'm happy, but I'm not happy on the right, and so I will decide to introduce another split over x2. So the threshold would be, let's say, t2, and so here now I will check whether x2 is less or higher than t2. So here on the left, which is less than t2, I will decide red, and on the right I will decide blue. Okay, and here I'm happy with my training example, and this will be my final decision. If I have a new sample, so I will decide based on this tree.
Hey, Thomas.
Yes.
If it's not complicated, can you tell what to do when you've got very high number of dimensions to select which one to split afterwards?
Yes, I will give. Indeed, the idea here is to indeed the problem is how to choose this feature and the threshold, and for that you need well, the basic idea is to choose that maximizing the loss reduction. So let's take an example. If you're in the regression task, maybe your loss function, natural loss function, would be the square error. And so so if you look at what you do at the root, so at the root you have only one value, and so of course the one minimizing this empirical mean of loss function would be the variance. So you will take as the estimate, so hat y for all samples would be the empirical mean, and the corresponding loss then would be the variance, just the variance. Okay, forget about the regularization term, and now you have to split first step. So here at the very beginning you have all your samples at the root, and next you need to split this sample, And so what you do is that you will go through all the features and find the threshold, look at the best threshold for each feature. And so for each such feature and each threshold, you have two subsets. So you have a partition, let's say A left and A right, so a partition of these samples. And of course, here, the best decision you can take, again, would be the empirical mean of that particular set. So let's say mu left and mu right. And so you have a reduction of the variance. You would have the linear combination of the variance on both sides, and then you take the best, basically. Okay, so you go through all features, all possible thresholds. So of course it may be expensive, and there are, I mean, we can discuss a bit that there are other ways to speed up this, but basically that's the idea. Okay. And so that is written here at any leaf. You have a subset of samples, and you have a variance. You find the split. So the split again is over all features and all possible thresholds, and you try to maximize the variance reduction. And in particular, it's with decision tree you can have an idea of the importance of each feature through the loss reduction. So here the variance reduction brought by your particular feature. So it's a way to explain your decision, because at the end you're able to decide which features were used to reduce your loss. So I will give an example a bit later. So this is for regression, and if you have classification tasks, so maybe your loss would be, well, you took the wrong decision. It could be 0 or 1, for instance, a binary loss. So at the root, the best value would be the mode, so the most popular label, let's say, and the corresponding loss would be the proportion of other labels. But then, if you do that, so you have your what happens on the root. But so you could do the same, trying to find the best split, A left and right, and taking the mode. But there are many different ways of doing that, especially if you have a large number of labels. And so actually, it's not a good criterion, you know, because here your decision would be based on only 2 labels, but there may be, I mean, 10 or 20 labels, and the repartition of the distribution of samples that are not that have different other labels would be arbitrary in a sense, that wouldn't change the loss. And so for classification, you actually use other metrics that are more, I mean, that allow you to converge more quickly to the good decision tree. And through a measure of diversity, how diverse are your partition of your set of training examples. And one such diversity measure is a Gini index. So it's actually 1 minus the Simpson index, or the sum of the square of probability. So it's the probability that if you take 2 samples, training examples, you sample them uniformly at random. It is a probability that they get different labels. Okay, it's a measure of diversity. You could use other measure. You could use, of course, entropy or other measures. But for instance, in scikit-learn, the default diversity metric is a Gini index.
Thomas?
Yes?
I think maybe it is very similar. I've seen the Gini index a bit differently written. So I have seen the Gini index written in a bit of a different form, but maybe it's very close.
Okay.
It's I've seen it about seen as a sum of k, pk times 1 minus pk.
It's the same actually.
Should be the same.
Yeah, the sum of pk is 1 actually. Okay.
Right.
Yeah. So it's the same.
It's the same, yes.
Absolutely. And so if you do the same, you play the same game with this as before. So actually you have your Gini index at the root, which is the diversity of all labels of your training examples. Now, the way you will split A in A left and A right will give you 2 Gini index. And of course, here, the way you split, I mean, all labels will matter, okay? You'd like to make, for instance, if you have 3 colors, let's say red, blue, and green, you try to have red and blue on the left and green on the right as far as possible, or other combinations, but you try to have a less diverse distribution of your labels. And again, you do that by looking at all features and all possible thresholds. So you don't have any possible partition. The partition are driven by the features, okay, by this X vector characterizing each training example. Okay, and so you do this recursively. So you look at the diversity reduction, and you do it. I mean, you may have a limit on the depth of your tree, but basically you can do it as long as you have a diversity reduction. Okay, and so here at the end, of course, you need to decide. So you build your tree based on your diversity. Maybe that tree, I don't know. And at the end, you take the majority. So decide what is the label on each leaf of your tree. You take the majority vote. So the label that is the most popular in the training, in the examples that you have in this leaf. Okay. So interesting observation is that if you have a binary classification, actually you can easily check that the variance is the Gini index, and actually it's if I come back to Anastasia's question, you can write this. You can also write this Gini index as so if at the sum, and if you have only 2 labels, so binary classification, this would be 2p1 minus p, where p is a proportion of 1, and 2p1 minus p is also 1 minus, let's say, how can I write it? This should be the variance. Yes, what is the variance? Sorry, yeah, the variance is this is a variance because the variance, if you look at the ones, you have a proportion p of ones, and there let me see. Yes. Is this? Well, I need to. Am I wrong here?
It's just 2 times.
Oh, no, sorry, yeah, it's 1 minus p squared. Okay, because this is their. So you need to decide 1 here. And so you take all labels having all examples having label 1, and your you have let me see. The mean is p, and so the square error is 1 minus p square, plus the same for the other. This would be p square, and so if you sum this should be p1 minus p. So maybe up to some factor 2. So let's say 2v should be j, if I'm not mistaken here. So essentially, when you do binary classification with a Gini index, it's equivalent to do regression, where you'd like to predict, just take 1 and 0 as values you'd like to predict, and your prediction is no longer a bit, it's a value between 0 and 1, and which can be interpreted as the probability of having labeled 1. Okay. So just an example. So before we move actually to ensemble methods, so the digits is a toy example you have in scikit-learn. So you have some small pictures of 8 by 8 pixels. These are levels of grays. Okay, so I think they are coded on one byte. I'm not sure, and there are so 10 labels. Okay. And here I split into train and test sets. So I will learn on this on 1,400 example, and the test to the accuracy of my prediction is based on 359 images. And so this is what you do with a decision tree. So you have it's a multi-class decision tree. So you may have what I mean by multi-class is that it's actually one tree, and you have your labels as leaf of your tree, and these are the results depending on the maximum depth of your tree. Okay, so 2, 5, or 10. So if you have a depth of 2, it means that at most you have so 3 decisions. So you can have a look at only 3 pixels, which are written here, and actually the intensity of this pixel corresponds to the feature importance. So probably the black, the darkest one corresponds to the one at the root. So you will first have a look at that pixel and then on the other one. And of course here you can only have 4 digits. You can only predict 4 labels. But surprisingly, the accuracy is not that bad. So that is average of all digits. So you have an accuracy of 30%, which is higher than 10%. That would be the one with the random guess. And if you increase the depth, so of course you increase your accuracy, but interestingly, you can have a look at what pixels matter in your decision. Okay, what are the most important pixels? So these are for multi-class decision trees, but you may decide to train binary decision trees with a one versus all strategy. So you'd like to specialize each decision tree to a particular digit, and you can play the same game. And here, what is quite surprising is that with only a depth of 2, your average accuracy of all digits is 95%. And here for that digit, for the 0, you have a look at what happens on the center of your picture, just because you can guess that probably if there is nothing in the middle, it's probably a 0. Any question on that before we move to?
I have a question, Thomas.
Yes.
Here you are building a decision tree based on pixels, and so we know that it's not so explainable, because if we look the matrices that you obtain, it's hard to understand why the machine decided to split the tree like this. And so I was wondering if you could inject or adapt this kind of algorithm to take into account more complex features, for example, the presence of segments or circle, and build a decision tree on top of this. For example, for if you know that there are 2 circles in the picture, it's probably a 8. If there is a single circle, this is a 6 or a 9 or something like this. I don't know if I'm clear.
Yes, so I choose. Well, first I must disagree on your first point. I mean, I think there is some explanation. I mean, if you have a neural net or SVM or whatever, you wouldn't have any information on the decision. It would be very hard to I mean, if you look at the weight of your neural net, for instance, it's very hard to decide which pixel matters in the decision. So here you have direct information of which, I mean, you have here at least, you know that with only 2 pixels, you can decide whether it's a 0 or not. So now you're right, for other digits, maybe it's a combination of pixels that matters. So I'm not sure you will find these circles and whatever, but you may find the pixel that matters. So maybe you need to do more, to work a bit more to find some pattern and so on. So of course here it's easy. I mean, you have only simple digits. Maybe if you have letters or you'd like to recognize all the patterns, it would be interesting to do this job. But so the idea is really that you have some information, okay, which can be specialized per digit. I don't know if it answers your question, Marco.
Yes and no. My question was, so I know that neural nets are complicated to explain. My question was rather if you have an a priori about the pattern on which you could do the splits, could you inject this in the machinery?
Okay, in the training.
Yeah, for example, you have a black box telling, okay, I am able to detect a circle, find the center, find the position, etc. So you have this kind of primitives, find segments, etc., etc. And instead of computing the gene index or the mean or whatever, you try to detect such patterns, and so you do a kind of kernel tricks, if you want, to build your decision tree. I was wondering if it was possible.
Yeah, I'm not an expert on that, but well, of course, here we talk about pictures, images, because this is example I've chosen. But actually, these methods are more on, let's say, I mean, regular data. Here you treat the picture as just a vector, right?
Right.
You don't have a look at the way these pixels are organized and so on. So, of course, for images, it's I mean, neural nets and convolutional nets and so on are more efficient. Okay, it's just a way to illustrate the explainability of these methods. But well, if you think of I don't know, if you think of there are some other data sets where you like to predict the price of a house maybe, and you can really see what the top 5 features that were able to that were I mean, significant for your decision. This is really the idea.
Okay.
Okay, so the first ensemble method is called bagging. So bagging is for contraction of bootstrapping and aggregation. And the idea is very simple, that you will train a multiple estimator for the same task. So the same training set. So you have all your training sets here. And so you like to have multiple ways to decide the output. And what you will do is to combine all this. So you will aggregate the decision of all of them. But of course, you don't want this agent or predictors to be clones. Okay, you'd like to have some diversity, and so this is the idea of bootstrapping. The idea is to use a subset of them, a subset of your training example, which you draw independently with replacements. So you will take a subset and train the first decision tree, let's say, with this first subset. Then you draw another one. You train the second with that one, and so on. So introduce diversity through the sampling of your in your training examples. But of course, you don't have an infinite number of training examples. This is the idea of bootstrapping. So you just hope that with this sampling, with replacement, you get some diversity. And at the end, you aggregate. So the aggregation depends on your task. If it's regression, maybe you will just take the average. If it's a binary classification, you take or any classification, you will take the majority vote, for instance. Okay, so it's written here. So basically, you have two key parameters, which are the number of estimators, number of trees, let's say, but well, it may be applied to other estimator than trees. Okay, but here I will take this example, which is the one you have with a random forest. Okay, random forest is a set of trees, hence the name. And the second parameter is the bootstrap sample size, how many samples you draw. And so with so this is basically the idea. It's very simple. With random forest, you introduce some additional randomness and diversity in your trees in sampling, or also a set of features that you allow for each split of your decision tree. So each one you have to split. Remember that you in a decision tree you go through all features. In a random forest, you will draw a subset of these features at random. So the number of features you sample is a parameter of your algorithm. And then at each leaf, you will select a different subset of these features. And for each tree, you do that. And so this introduces some diversity. And with extra tree, so extra tree is extremely randomized trees. So in this case, you take just random features and even random thresholds. So there are some parameters. So you are even more random. But it's easier to train because you don't have to select the optimal threshold. So you can have more trees for the same computational cost, and to gain it through the aggregation. At the end, you will aggregate and so decrease the variance of your prediction, basically. Okay, so I don't know if you have a question on that. The idea is very simple. And the when you use decision trees, so as in random forest or extra trees, again you can average the feature importance that you have per tree to get the feature importance. So the importance of each feature in the overall prediction, which is a set of trees. So random forest, for instance. Okay, so this is an example of what you get for random forest. So here the tree depth, maximum depth is 5. So if you have only one estimator, that would be a decision tree. Well, except that you don't allow, remember that with random forest, you don't allow to go through all features. So it's a sort of a suboptimal tree. And the accuracy is much it's more or less that you would get with a single tree, and this is the feature importance for all the digits. And now if you move to 20 estimator, the default value, for instance, in scikit-learn is 100. So with 20 estimators, you have a much higher accuracy of 94%, and they are the pixels that matter. But this is for all your digits, because remember that here it's a multi-class random forest, which means that for each decision tree you have all the labels that are possible. And again, you can do that with the binary random trees, and here the accuracy is even higher, and these are the feature importance for the digit 0. Okay, so only for 0. So here you focus on what happens on the center. Do I have a pixel here? And also then you look at where you expect zeros to your digit 0 to be in the picture.
Thomas, I didn't get what is the number of estimators?
It's a number of trees of your forest, basically.
Ah, okay.
Yeah.
Okay.
Okay, and so that's actually very simple idea. And the second family of ensemble method is known as gradient boosting. It's very different, actually. And the idea is to improve your estimator sequentially. So the previous method, bagging, was I mean, you could train your trees in parallel, okay, which is a nice characteristic of these methods. So here you will do this sequentially, and you'd like to improve your estimator looking at its errors. So let's say you'd like to predict y, and your decision at the end, if you are on your regression task, is a y hat. So you could look at basically the error you made, which is a y hat minus y. And so you'd like to, maybe what you will do is to train another tree whose objective will not to predict y, but to predict the error. Okay. And so you will correct the previous estimator, and so you will sum basically the output of these trees instead of averaging. Okay, so this is the idea here. So you have here basically a single parameter, which is a number of estimator. And so sequentially, what you will do is that you will take your current output, which is given by this f. So f is the output of the current estimator, which can be that of a single tree, or if you don't have any tree, it could be, I don't know, if you're in a regression task, it could be the mean of your values. And then you will train h, which you will add to your previous estimator. And h, the job of h will be to predict this error. So it's as if your samples were this x and the errors y minus y hat. Okay, so the idea is also quite simple. I need to explain why it's termed gradient boosting. So it's a boosting because you boost at each step the previous estimator. The gradient comes from the fact that well, this y minus fx, so this residual, are here can be considered as the gradient of the square loss function, but I will come back to this a bit later. There are many ways to, many variants of this idea. First, you may add learning rates. So you would just add a parameter here at less than 1, so that you will give less importance to the new prediction, okay, to avoid oscillation or to make your estimator more robust. You may add weights. You may have a look at your samples and give more weight to those where your prediction is incorrect, is very bad. Okay, and this is basically the idea of ADA boost. So ADA is for adaptive boosting. Okay, so there are some variants on that. And this is what you get using the scikit-learn implementation of gradient boosting. So again, you get a similar, quite good accuracy. And again, you can look at the feature importance. If you use decision trees, you just average at the end your the gain and the loss of each feature. Now, XGBoost. So XGBoost is a particular case of gradient boosting. It's a quite recent algorithm, and it's one of the top algorithms in many machine learning competition. Okay, it turned out that it's very efficient in general and very robust. And so there are a couple of details that that change here. So the idea is the same. Basically, you will learn sequentially. Okay, so you will learn sequentially a regression tree. So I need to mention maybe before that due to the fact that you sum, okay, you correct the previous decision, you cannot apply this to multi-class classification. You can apply this to either a regression task or a binary classification, okay? Viewing the label 1 or 0 as a value to predict. And if you have multiple labels, what you do is that you decompose this as a multiple binary classification tasks in one versus all task, okay? Just forgot to mention that. So here it's the same. Actually, you do everything is like a regression task. You'd like to predict a value, which may be binary. And so you will learn sequentially this regression tree. And so here you correct the error. Okay, so these were your previous output, and you will add something. You will correct the previous prediction. And here, what is characteristic of this XGBoost is that you will add a penalization, so regularization term that depends on your particular regression tree. So basically, at each new step of your algorithm, you will consider regularization term that apply to that function h, that is whose objective is again to correct the previous error. And what you do is that since this problem is not so easy to solve, you will use a second order Taylor expansion of your loss function. Okay, and a particular regularization function, which is at the bottom here. So remember that H is a regression tree. So basically, it's a simple function in the sense that you have a partition of your set of samples. So to this, let's say, AL sets. So AL are subset of your training samples. And for this particular set, you will apply this function alpha L. Okay, so for A1, you apply alpha 1 and so on. And now your regularization function, you have a term which is related to the variance of the different values you have, the alphas, and plus a constant term, so that each time you add a leaf, so you split a leaf, you have a fixed cost, gamma. Okay. And what is nice is that if you combine these two, due to the fact that your H function is a particular function that is simple here, you can write this loss function is in a more compact form as a sum over the leaf of your tree. Okay, you need to minimize this particular function. Believe me, maybe you can do the. You can have a look at the XGBoost paper if you want, but it's quite easy. And this J and H term are just the sum of the gradient, or let's say the first and second derivative of the loss function, which you have at the very beginning. It depends on your function. I will give an example later. And so what is nice is that now, if you'd like to solve this, you need to solve this function. So remember that we look for H. So you need to find this alpha and this A, this sets A. So at least you can solve in alpha. Okay, solving in alpha here is very easy. Okay, and so you find this explicit value for alpha star. And so at the end, you just need to find the optimal partition of A, minimizing this cost function. And that's the end of the story, because if you remember the way the decision trees or regression trees are built, you have a loss function, which may be the square error, which may be the Gini index. Okay, so here you just apply the same tricks as the same idea of recursive split, but your loss function is that one, is that particular one, and it's built based on the error, in particular through the first and second derivative. So you have a second order approximation of what happens around your prediction. And it is the way you build this new tree. Okay. So I don't know if you have questions at this stage.
Yeah, Thomas?
Yes.
Yeah, it's quite clear. I mean, one has to, of course, go through all the steps, but sometimes, you know, even the second order Taylor expansion can have a significant error depending on how far the H correction term is from the point where you start. So I was wondering if some extreme cases can completely, go outside, let's say, the attraction area of the solution.
Yeah,
something very strange.
Actually, it really depends on your loss function, and you have the choice of your loss function. So it's if you choose something that is very, that is not smooth and so on, you may have some bad estimate. So, but if you look at XGBoost, the Python library, for instance, so you have a subset of loss function that are proposed for which you know that the approximation is relevant.
Okay, so they have some kind of bound for the from the third term and so on.
So here as an example, if you just take the square error. So
okay, yes, of course, yes.
Yes. And for classification, you can take the log likelihood, and again with the sigmoid, and again you get this usual approximation, and it turns out to work quite well.
Yeah. Okay. I see. Yeah, these examples are very clean in the sense that you don't have
but there are more, complex loss function. But you're right.
Exponential, for example. I mean.
Yeah, I'm not sure. Yeah, you have to do the computation and so on. Just have a look at the loss function that are proposed in XGBoost, for instance. There are not many, but let's say more than that. And but it's true that the choice depends on the fact that you have a good second order approximation. And that's it. So here, so of course these are very simple, very basic example. This digit data set, but it really works extremely well in many different tasks, and it's quite fast. Here, what is interesting on this example is that the feature importance look quite similar, but well, they differ in a sense between XGBoost and gradient boosting. And they are quite different from random forest, for instance. So well, that's an interesting observation, I think. So that's it. Just have to keep in mind that there are two families of ensemble methods that are very different. So bagging, where you do parallel training and you aggregate, and boosting, gradient boosting, where you do sequential training one after the other, and you try to correct the previous errors using the gradient, basically, or second order approximation with XGBoost. There are other very efficient and both in terms of quality and computation time, gradient boosting methods like light GBM, light gradient boosting machine, that are basically where there are many different features, but one of them is the fact that you use histogram to compute the optimal threshold. You pre-compute. You put your samples for each feature in some bins using some histogram, and so you use integer. You have fast ways to decide the threshold. So you decide between a fixed number of a value for your threshold. So it's like a discretization step that helps a lot in the training of your decision trees. And XGBoost. So XGBoost is for categorical gradient boosting. The way to when you have categories, let's say I don't know, a color, for instance, a color cannot really be represented by a number. So you have 10 colors. So how do you proceed to put them in your tree? Because you, so far I've used numerical values, and so both light GBM and XGBoost provide ways to handle these categorical features. Okay, that's it. I don't know if you have questions.
Thank you.
Yes, maybe Thomas.
Yes.
So you presented trees in the context, ensemble methods in the context of trees and forests, and I'm reading many ensemble methods that combine or that are just a majority votings on the output of other models that are not forests, like neural networks. So do you know if it's fair when people mention, is ensemble are ensemble methods just for trees, or is it something that is more general?
No. It's well, these ideas could be applied to other predictors, right? I'm not aware of I don't know how you call a set of neural nets, like it wouldn't be a forest, but a population of of brains. I don't know. But of course, the idea here is that it's quite fast to train, and it's explainable in a sense that it's well, that's but yeah, the idea of bagging and boosting is not limited to trees. You're right.
Yeah,
Yeah.
I have a question. So it's a fuzzy question. Based on the experiments you tried, do you have a favorite in terms of trade-off between speed and efficiency, or is the answer it depends?
I haven't tried really. I think I haven't tried with million of examples, but really the top ones you see on in the blogs and in the competition, I would say XGBoost or LightGBM.
Okay. And even in terms of speed, because sometimes you don't want to wait 2 weeks before getting an answer.
Yeah, there are many parameters like the number of the depth of your tree, the number of estimators. So you can trade off speed and complexity. Well, so if it's too long, you just try to tune these parameters.
Okay.
Yeah, but LightGBM I think is quite fast because the training of each individual tree is fast.
Good.
And yeah, actually XGBoost is not in scikit-learn library. There is a wrapper so that you get the same API as scikit-learn, but it's not inside it, scikit-learn. And LightGBM, I'm not sure.
Okay.
Actually, this idea of how to handle categorical features is quite interesting. And if you think of text, I know you're interested in text.
Yeah.
If you think of words as categories, for instance, so XGBoost so claim that to be able to handle these features with and a combination of numerical features and categorical features. So I think it would be nice to, have a look. So maybe it would be the topic of the next Reddit group, how to, the best predictors for categorical features or a mix of numerical and categorical features.
Thanks. Okay, so maybe I will stop the recording actually.